Thermodynamics video number 5, and we're looking at entropy. Now, entropy is one of the most interesting things that we look at in chemistry. It's a fine bit of physics. It's a measure of disorder. Now, most people can imagine that disorder is a thing. Most of us encounter quite a lot of disorder as we go through our lives, but the fact that you can put a number on it and say how disordered something is, it usually surprises people. It comes from statistics. If I have a substance which is made up of 5 particles, and those 5 particles are organized in neat rows and columns, there's very few ways in which I can order those particles in that situation. So the amount of the variety of ways of organizing them corresponds to the disorder. If I put those 5 particles into a larger container and spread them out randomly, then suddenly the number of ways I can organize those 5 particles increases a great deal. So we'd expect solids to be very organized particles, therefore low entropy, and gases, or liquids and gases, to have very high entropy. So if we were to draw a graph of entropy for a substance, and we slowly heated it up to temperature, is we're going to be measuring in Kelvin here, and then measuring the amount of entropy that a substance has. 0 Kelvin, we'd have 0 entropy. You can't have any disorder if particles don't have any energy. And then it would go up a bit. When we hit the melting point of our substance, the amount of entropy would go up a lot. And then when we hit the boiling point, the amount of entropy keeps on going up, would go up a lot more. So this would be the melting point here, and this would be the boiling point here. So entropy always goes up with temperature. It's reliant on temperature, but it jumps up when we change phase. Okay, so just having a look at the topic booklet here, it reminds us that the second law of thermodynamics, I don't know how familiar you are with your laws of thermodynamics, but maybe look them up. Any spontaneous process increases the disorder of the universe. So this idea of a process being spontaneous, we're using that word in a very specialized way. It doesn't mean that you decide to have a party suddenly and go out and have a great time. It means that a process can happen thermodynamically. Thermodynamically, that's a long word. In other words, we wouldn't have to input any energy in order to make that change happen. Now we have to be a little bit careful with spontaneous processes. It doesn't give us any idea of activation energy. So as far as we're concerned, a process is spontaneous if it's downhill as far as the universe is concerned. It's exothermic and it increases entropy. So an increase in entropy makes processes more spontaneous, more likely to be spontaneous. I'll put an exact definition up when we get to it. Okay, so that's a real introduction to entropy. It's measure of disorder. It goes up with temperature, and liquids and gases would have more entropy than solids. Okay, so how do we calculate entropy change? Well, first of all, it helps to be able to spot an increase in entropy or a decrease in entropy in an equation. So if we just look at an equation, and I've got the That's 5 O2s rather than 502. 4 NO, and look at an equation like this. A simple way to spot an increase in entropy, these are all gases by the way, that's relevant. A simple way to spot an increase in entropy is just simply look at the number of entities that are in the reactants and products. So on the left here I've got 9 entities, and over here I've got 10. So what that tells us is there's an increase in the number of entities, so therefore there's probably an increase in entropy as well. The word entity, it's an odd word. It just means things, molecules, ions, atoms, anything can be an entity. It's just a good grouping word. Okay, so that's one way of spotting an increase in entropy is when we have an increase in the number of entities. Another way is to look at the states. So here's the other equation that I've put in the topic booklet. So if I react sodium chloride with sodium hydroxide and make ammonia, let's assume everything's in its standard state here. So we'll have 2 solids reacting to make a gas and a liquid. So first up, I've got an increase in the number of entities. I've gone from 2 things to 3 things. So you would expect entropy to increase there. But in addition, I've gone from solids on the left to gas and liquid on the right. So that also implies there's going to be an increase in entropy there. So those 2 things are kind of giveaways. Increase in the number of substances produced, or the number of entities, and an increase in the amount of liquid or gas that I have on the right hand side. One more example, thank you. And this answers the question that I asked yesterday in the last video. Depends when you watched it, doesn't it? Aqueous ions, I don't know if you think about aqueous ions, they're spaced out quite a lot and they're moving quite randomly and quite quickly. So aqueous ions are a bit like gas particles in the random way they behave. So if I go from a solid to 2 moles of aqueous entities, so 1 mole of solid, 2 moles of aqueous, that's definitely going to be an increase in entropy there. It's quite a big increase in entropy. And that's why substances will dissolve endothermically, because the endothermic change that's requiring energy is overcome by the entropy change, which is going up, which is the way the universe likes it. And again, there is a strict mathematical way of combining these 2 features, but we'll do one thing at a time. Okay, so calculating entropy change is similar to calculating enthalpy change. You'll remember delta H is a measure of enthalpy change. Delta S is our measure of entropy change. So delta S, it's just the sum of the entropies of the products minus the sum of entropies of the reactants. In that way, it's very similar to the measure of delta H using delta HF data, products minus reactants. Okay, so there's a example. We're just going to follow this one through straight from the booklet here. So this is the extraction of iron, or the reduction of iron from iron oxide. Making iron, metal and carbon dioxide gas. So delta S will be products minus reactants. So the products are iron. Should just write these on here. These are the entropy values: 27.3, 213.6. Carbon Notice that solid carbon has a very low entropy value, 87.4. There we go. So it's 4 lots of 27.3. I've just seen that in the booklet. It's not completely right, is it? 3 lots of CO2. That's right. 3. Take away, what's going to be all of, 2 lots of 87.4 and 3 lots of 5.7. Unlike delta HF, elements don't have zero entropy. Pretty much nothing has zero entropy unless it's sitting at 0 degrees Kelvin. Okay, so the correct value for that comes to 558.1. Notice the units, so of course the units of delta H is kilojoules per mole, units of entropy, joules, and that's going to trip us up later if we're not careful, per Kelvin per mole. So that's that's a big increase in entropy. Well, we'd expect that, wouldn't we? We've gone from 5 moles of solid entities to 7 moles of entities, 4 of which are solid, but the other 3 are gas. So more entities, and we've made a gas. So entropy on our side in this reaction.